and welcome back to this lecture series on noise control in mechanical system with myself Professor Sneha Singh from IIT Roorkee. So we have begun our module on noise in mechanical systems, and so far what we have discussed is we have studied about what are the types of noise typically found in the mechanical system. So you have like the structure-borne, air-borne, and the fluid-borne, these kind of typical noise, types of noise available, and then what are the types of noise in some of the common mechanical systems and their noise sources, such as the noise sources in a engine, in a rotational machinery, in fans and compressors. What are the typical phenomenon through which the noise is created, and what kind of noise is present, what is the frequency and the temporal content of these noise sources within the mechanical systems and mechanical subcomponents. And then we have also discussed about the mechanism of noise generation in these various mechanical devices. Okay. So, in this lecture we will study about the structure-borne noise and air-borne noise in more detail, because these are the two types of the most common categorization of the types of noise that are available in mechanical systems, and each of them they have a different means of propagating and spreading, and therefore they need different types of noise control techniques. So, we will discuss about these things in this lecture. So, quickly to recap, the types of noise present in mechanical systems can be divided based on how they propagate through, and we have the structure-borne noise, air-borne noise and the fluid-borne noise. So, let us study out of this, these two are one of the most common forms of noise propagation in mechanical systems, and then we have the fluid-borne as well, but the mechanism of fluid-borne noise is more complicated and is kept out of scope of this particular lecture series. So, let us see the structure-borne noise. So, what is the definition here? Here these are the sound waves which propagate through the solid material, like you can have the material of the wall, floor or any kind of the body of the machinery, and it moves within these structures in the form of typically as fractional vibrations. So, let us say this was some kind of a source and attached to a long kind of a plate or a mount, and this created the noise, and this noise propagated in the form of the vibrations of this plate, the fractional vibrations, and then later you have a receiver here, and from here then it radiated outwards and reached the listener. And we have already studied about the radiation phenomenon and how the plates or solid structures, they can radiate the longitudinal sound waves based on the flexural waves created in their structure. So, here what happens, the waves they typically propagate through the solid structure and in the form of like flexural vibrations or other forms of vibrations, and then after a certain threshold they start radiating outwards into the surrounding acoustic medium or the fluid media, and then it can be caught by the listeners as the audible noise. What are the typical origin of structure-borne noise in mechanical systems? We have, it can start, let us say, in the form of, let us say, mechanical impact or the vibration of a motor which is mounted on some kind of solid structure, then the turbine that might be mounted on some solid structure, or any kind of machinery that is kept on the ground or is kept in contact with some kind of solid structure or frame. Then if it starts to vibrate and create the noise, that vibration comes into contact with the mount or the stand of the machinery, and through those mounts and stands also it propagates as a structure-borne noise. In the same way, if a machinery is kept on a hard floor, then most of the noise coming out of the machinery is going to radiate through the ground on which it is kept or the hard floor on which it is kept in the form of structure-borne noise. Okay, so basically anything where the solid structures, they are coming in contact, and the sound waves, when the noise is created, it is finding a pathway in terms of these solid structures to go through. So mechanical impact hammering at a distance of connected surfaces can create vibrations throughout the structure, and imbalanced masses from some rotating shaft, it can again create the vibrations, and if that shaft is connected through the bearing to the other parts of machinery or some other solid structures in the machinery, then that same vibrational noise will pass in the form of vibration through the various interconnected structures and then propagate through. So, one typical observation what you will see is that suppose you have a speaker at your home, just a simple observation. If you are playing the speaker through the air, just hanging on like through some cables, and then you drop that speaker on a hard floor and you play the same speaker, you will hear a much louder sound when you play the speaker on the hard floor. Why? Because when that same speaker is hanging on the cable in the air, it is whatever noise is being created due to the movement of the diaphragm of the speaker, that is directly radiating into the air. So, this is a airborne noise. But when that same speaker is coming in contact with the hard floor or some kind of hard surface where it is kept, then the vibration of that speaker has another means of propagating. So, whatever is the hard floor or the hard surface on which the speaker is kept, the noise created will then pass on as the vibrations in that hard surface, and now we will have structure-borne noise as well in comparison to the airborne noise. And as you will see, the structure-borne noise, they usually have more problems in attenuating. Okay, they don't attenuate so easily over distance, and compared to the airborne noise, they have less attenuation over distance. So, in this case, when the speaker is kept on a hard surface, some part of the noise is propagating as structure-borne noise and it's not attenuating, and it is much louder to hear. So, what are the transmission path of this structure-borne noise? Obviously, any kind of solid structures you can think of, like the metal beams in the mechanical system. Suppose some kind of building is there, then the concrete and the beams and the frames of the building or kind of structure, and they can travel over very long distances and they can be heard very far away from the original source. Okay. So, they suffer less attenuation, okay. There is less energy attenuation and they can travel over very long distances through these interconnecting structures, and even if the noise is produced much farther away, but because they are getting these interconnected structures to pass through, they can be heard much louder even at longer distances. So, they are more dangerous in terms of noise. The frequency content, usually when typically the kind of structural elements we use in mechanical systems or even in the civil structures, so most of the engineering materials, they have their natural frequency, or the parts that we deal with, the natural frequency is usually in the lower end. So, the structure-borne noise typically propagates through these structures at lower frequencies. So, that becomes a typical content, which is the lower frequencies, and then it can cover a wide range depending on the source, but mostly it is on the lower frequency end. And as I told you, the transmission efficiency, because it travels through the solid structures, usually there is much less energy attenuation compared to the airborne. So, they can be heard much louder even at further distances. Let us see the airborne noise in comparison to structure-borne. So, again what happens here? So, in the previous case you had some noise source which found some pathway through the structures and propagated by the means of vibrations in the structure, and finally after a certain point or after a certain threshold it radiated outwards into the air and was heard by the listener. So, the structural elements were one of the major path through which the sound wave was propagating. But in the airborne, whatever is your noise source, so let us say you have some noise source, let us say we have a typical example of a person speaking and then there is another listener. So, like for example, I am speaking to you. So, the person is speaking and is creating these speech signals. They are radiating directly into the air. There is no structural pathway here. Directly from the source they are radiating, so directly from the source they are going into the fluid acoustic medium and are radiating forward as a longitudinal acoustic waves. So that becomes your airborne sound. So directly from the source they are almost all part of the sound that is created from the source is directly going into the air, and then it is being received by the receiver, and there is not significant involvement of structural elements in the pathway. Okay. So for example, the conversations you have, the if somebody is playing the guitar, once again that is a airborne sound. Some of the machine tools, they are creating the sound which is propagating outwards in the air. So usually what happens is that it comes directly from the source into the surrounding environment, like the vehicle horns, the speech, the music, etc. All of these are example of airborne noise. So what is the transmission path here? Obviously the transmission path here is the fluid acoustic medium, the most common being the air or the atmosphere that we live in. Okay, so air is one of the most common medium through which these sound waves are propagating. So what happens when the sound waves are propagating through the air? There could be various obstacles on their pathway. They can find some obstacles like walls, barriers and other such materials which might be able to reflect, absorb or transmit a portion of the sound waves that are incident, and hence these airborne sound waves, they get attenuated because in our surroundings, in our atmosphere and in our environment, whenever there is a noise source and the sound waves are propagating, definitely they are going to encounter various kind of materials and obstructions in the pathway. Okay, it could be in the form of some object that might be present, some person might be standing, there could be walls or the buildings, the trees, anything that is present in the atmosphere will be able to reflect and deflect some form of the sound waves, and hence because of this the attenuation keeps happening over distances. And not just the presence of these objects which are in the atmosphere, even the air itself has its own resistance. So if I am speaking, there is a air resistance, and slowly over long distances it is going to attenuate the sound waves. So in comparison to structure-borne, the airborne noise will definitely face a lot more opposition and a lot more kind of obstruction compared to structure-borne, and hence it will be attenuated more. There will be more attenuation in general of the airborne noise over large distances. And the frequency content for structure-borne was typically low frequencies, but here it is in all the audible frequencies that you can imagine. You have the airborne noise. The transmission efficiency, obviously the energy is lost much faster. So as I told you again, the attenuation suffered by the airborne noise is much more compared to structure-borne, because the sound wave gets to interact with a lot of things in the pathway, the barriers, walls, absorbers and lot of other things. So let us see how to control these two different types of noise, the structure-borne and the airborne. And in the typical module on the noise control and the principles of noise control, I had told you that if you want to control the noise, you can do that using the source path receiver model, which means that you either modify the source, which is the most efficient and effective method. You simply change the source or redesign your source that it ends up creating less noise. Otherwise, if you don't have that option, the machinery has been installed and now you are going there as a noise control engineer, then changing the machinery, if that is not an option, then you will modify the pathway. And then finally you can modify the receiver, which means you can give some ear plugs or mufflers to the receiver or enclose the receiver and isolate the receiver from the source. But path modification then becomes one of the most common method, and in the path modification, structure-borne has a different pathway and the airborne has a different pathway. So obviously the control measures will then change because they are having different kind of transmission paths and different transmission strategies. Let's quickly recap on the overview of how the noise control is done. It could be active or passive. Active is when external energy is needed and There are technologies through which you create an anti-phase noise to reduce your unwanted sound, and then passive technologies where no external energy needed, some acoustic enclosures, barriers, dampers or isolators. So basically some passive materials and devices are used to attenuate the noise. And for any mechanical system, the role of maintenance becomes very important, because if the machinery is brand new or is in a very good condition, is properly lubricated and properly fixed and installed with no loose ends, it will run much smoothly. There will be much less unwanted vibrations, there will be less of unbalanced forces, and therefore there will be less noise created. So a best way would be to have a regular maintenance of the machineries in order to ensure its quiet operation by preventing the component wear and tear, reducing the friction and the vibrations, avoiding the failures and the downtimes, and always making sure that in the plant or in the site where these machineries or mechanical systems have been installed, you have a proper condition monitoring and regular maintenance checks, and the lubrication, the tightening, replacing of the worn out components, and adjusting the alignment of the misaligned parts, debris removal, monitoring of the excess vibration levels, and all this, if they are done, then the machinery is going to function smoothly and it will create less noise. So I had already told, like in the previous lectures, that the smoother is the function of any machinery or any kind of mechanical system. The less obstruction or the less resistance they face to their smooth operation, the less would be the noise, and the more resistance or the more obstruction they face to their smooth functioning, the more is going to be the noise created. So with this overview of the typical noise control strategy for mechanical systems, let us see the differences in controlling structure-borne noise and airborne noise. When we are talking about structure-borne noise, then it propagates through, as I told you that as a noise control engineer, if you cannot modify the source, then you have to modify the pathway. And in the case of structure-borne noise, the pathway are these solid structural elements, and it is propagating as vibrations through these structural elements. So the main noise control strategy would be to control this vibration transmission through these interconnecting kind of pathways. Okay, whatever is the structural path that the noise is taking, you have to control the vibration transmission through this. Various kind of measures like vibration isolators could be used and installed in the pathway, in the major pathway of the noise between the noise source and the listener, damping techniques and installation and maintenance. Let's quickly have a look at one by one at these strategies. So the first one is vibration isolation. What do you do here is that here isolation means that from the schematic I can show you, this is your noise source, the source that is creating the noise, and this is, let us say, your receiver who is going to receive it. You have some pathways. It could be in the forms of the mounts of the machineries or the frames and stands or any kind of other structural elements that are present in between the noise source and the receiver, and your major noise source is propagating through these pathways like this. Okay, it is propagating as structure-borne noise. So what you would do is you would modify this pathway. So vibration isolation here, principle of vibration isolation or the philosophy is that you change the pathway so that it is able to isolate or stop the transmission from the source to the receiver. Okay, so whatever vibrations were going this way, suddenly suppose some kind of isolating devices you have installed in the pathway, these. So what will they do is that they will isolate the vibrations. So whatever vibrations were traveling, they will damp out, then again more damp, and by the time they reach this end, they would flatten out. So you isolate the vibration between the source and the receiver. Okay, so preventing the transmission of the vibration waves generated from the source to the surrounding structure through which it might propagate. And how can you do that? You usually place resilient materials because they do not transmit the vibration in a very good way. Okay, so whatever structure that is surrounding your source, you can make it with the materials that are known to be more vibration resilient, i.e. the materials which are known to dampen the vibrations. They are not very good conductor of vibrations, if you can say. Okay, just like we have thermal insulators or the electrical insulators, we can think of this vibration isolators as kind of vibration insulators. So, these are those materials which will sort of reduce the flow of vibrations. They are very resilient and they do not conduct the vibration very easily. So, that kind of material you can use. For example, some of the composite materials are known to be more vibration resilient compared to the metals. Okay, and all of this can help in interrupting or stopping the transmission. Then you can redesign your structural path. You can install some of these mass spring systems or isolators, such as the rubber mounts, the springs and the special plastic pads in between the source and the structure. So, whatever, let us say this is your structure, you can have these isolating elements in the structure. Okay. So, you can sort of break the pathway by installing at regular intervals these breaks such as rubber mounts, springs or plastic pads. It will break the path of the vibration. Okay. So, what do these materials do is that they absorb the vibration energy and they lower down the amplitude before transmitting it to the other end of the structure. So, this shows some of the examples. Here we have a machinery, it is directly installed on the ground, but at the connection points these spring type vibration isolators have been put, and the main purpose is that if the vibrations are generated here, they would not propagate over here. So, they would be blocked by this and will not go there. Okay, from the machinery to the ground structure. So, rubber pads, springs, various kind of elastic mounts are also available, and all of these are known to stop the flow of vibration. Now, the other technique is damping. So, just like we have vibration isolation, the other one is damping of the vibration. There is a difference between isolation and damping. What does isolation mean is that stopping the transmission of the vibration waves. So, you can have these isolation devices along the pathway and they can stop the transmission of the vibration waves. But damping means a means through which the vibrational energy can be dissipated in the form of heat. So, some kind of frictional elements you can think of, some kind of means, some kind of frictional devices. If the vibration is passing through them, then due to the friction faced, the vibrational energy is converting into the heat energy and is dissipating in the atmosphere, and that is leading to the loss of energy. So, they typically dissipate the vibration energy as heat, and in that process they help in reducing the vibrations pass on through the structure. Typically, the viscoelastic materials are one of the most common damping materials used. For example, the various kind of rubbers and composite materials, they tend to be better damping material. They tend to dissipate, they sort of can be thought of as more resistive to the flow of vibration, and they convert the vibrational energy into friction and heat. So, these kind of materials can be used which are damping materials. So, a difference needs to be understood here is that isolation is simply stopping the waves and damping is converting it into heat energy. The third major form of technique is proper installation and maintenance. As already told, any part, just think of it as an observer. Suppose you have any machinery, just go near it and you can see, suppose some part is vibrating. There is most likely it is a loose part which is not properly fixed and it is able to vibrate. Suppose you could tighten that part using a screw. Even in any kind of machinery which is old and worn out and a lot of vibration is happening on some parts, if you just go and tighten those parts with proper screws or fix these parts properly, then suddenly the vibration is going to go down a lot. So, that installation and maintenance again plays a very important role in reducing the vibrations, proper mounting, proper reducing of the misalignments, lubrications, proper fixing and tightening of the materials, making sure that there is no loose ends, etc. all of this can help in reducing vibration. Now, how do we control the airborne noise? Airborne noise typically travels through the air as sound waves, and already a long module was dedicated in this lecture series on noise control, and we studied about the various passive noise control devices such as the barriers and the absorbers, and within the absorbers we studied about porous materials, Helmholtz resonators and all barriers and closures, these kind of devices. So, all of that was a means of controlling airborne noise. So, we have already discussed in depth about how we control the airborne noise. What you do is, because a sound wave is traveling through the air, you keep installing more structures that can act as obstructions to the flow of the sound waves. Okay? And these structures could either be barriers which are going to reflect back the sound waves, or they could be absorbers which are going to absorb and convert the sound energy into heat. Various kind of absorbers we have seen, like the porous materials, the Helmholtz resonators, the acoustic metamaterials and perforated panels, micro perforated panels, all of these are resonance based sound absorbers. And similarly, the barriers and enclosures, they are all methods of controlling airborne noise. Especially you can see that in the exhaust and the engine noise, it can be reduced by having mufflers and silencers which are installed literally in every tailpipe of a vehicle. So, what are these porous materials? Again, they convert the sound energy into, they dissipate the sound energy as heat. Why? Because the sound wave faces more obstructions to the various pores and the fibers within these kind of materials, which converts the sound waves into heat, and we have discussed in detail about these porous materials and their method of operation, which can be referred to in the previous lectures. And what has been observed is that these porous materials, they are more effective in high and mid frequency noise control, and some of the most common porous materials that you find is the fiberglass is like amongst the most widely used industrial porous material. Okay, it is very widely used in industries, in most of the building applications for soundproofing purposes. Then these days even foams, and by foams you have open cell foams. Okay, there could be, when you see, you get in the market commercially you can find open cell, closed cell and so on, but open cell foams are the ones that would be handy because they are the ones that would act as absorbers. They would have to allow the sound waves to enter inside and get dissipated. So, the open cell foams, they are usually used in the appliances and the machineries. Then mineral wool is also being used a lot these days in walls, ceilings and the floors to absorb the sound and improve the insulation of buildings and indoor spaces. So, in the room acoustics, they are being used for offices, studios, auditoriums in the form of acoustic panels, baffles and the ceiling tiles. The enclosures, they are mostly used in the industrial plants for enclosing the machineries or the equipments. Okay. Then resonators obviously are being used specially for, because these porous materials are more commonly used to control high and mid frequency noise. So, for targeted low frequency noise control, resonators are being used. It could be Helmholtz resonator or the perforated panel or the micro perforated panel or the acoustic metamaterial. All of these are a means of controlling low frequency noise. They use the resonance phenomenon and they are able to achieve the sound wave attenuation. And they are now being applied these days even in the automotive exhaust system, where you have the silencer, and in the silencer you can find perforated panels, then Helmholtz resonators and various kind of expansion chambers that act as resonators. So, typically these are used in these automotive exhaust systems. Even in some of the newly designed enclosures, they are being incorporated, and in some of the newly designed acoustic barriers, now we are incorporating these resonator based. So, these are the new technology that are coming up, like the local resonance sonic crystal acoustic barrier that is now being used. The mufflers and the silencers already told about. In the exhaust and the engine you can see them, and they are having various kind of compartments with perforations. The perforations help in the thermoviscous losses, and then we have the Helmholtz cavity, which also helps in resonance based sound absorption, and they are applied in the vehicles and the industrial equipment wherever we are making use of the exhaust and the engine. So, the acoustic barriers and the enclosures used for airborne noise control, and such as concrete, made of concrete, bricks or other kind of sound proof materials, barriers are there. Especially you can find in the highways, these highway barriers are there, and even there are barriers in the construction sites or enclosures in the construction sites. These are the images taken from around the campus of IIT Roorkee, where you can see that these barriers are installed wherever the construction is happening, so that they can contain the noise within the construction site and stop them from propagating outside to the other residential and quieter areas. In the same way, the transformer rooms are always enclosed completely using these enclosures, and all of these are methods of controlling airborne noise. So, this is a quick summary of whatever has been taught in this lecture, which could be used as a go-to guide for any noise control engineer. So, for the structure-borne noise, the medium is these solid structures, walls, floors and the machinery parts. Airborne noise, it is air. The source is usually the vibration of the structures or the components, but here the source is that directly the sound waves are radiating from whatever is your machinery or person. In the control methods, we basically have isolation. So, we try to stop the vibration from propagating through. So, we can either isolate it or we can damp it. And then in the control methods here, we can install obstructions in the pathway. In the air, we could have barriers, enclosures, resonators and various other soundproofing materials. And the frequency range here is lower, and here we have mid to high frequencies in the airborne case. The challenges are that it travels over long distance with much less attenuation and is much harder to control. And here the challenge is that even a small gap in your enclosure or even a small gap, and it is going to propagate through. So, the things need to be properly sealed here. So, with this I would like to close the lecture. Thank you for listening.